Hello, folks. So, right now we are going to start to look at the parts of the atom again. We're going to look at how, on a less historical approach and more on a more theoretical and understanding approach to the atom and elements before we move on to a greater knowledge. Go ahead and get started. So, as we talked about previously when we looked at the history, atoms are made out of protons, neutrons, and electrons. When we talk about them, we'll use the term symbology of P, N, and E. Now, generally speaking, when we talk about the charge of each, a proton will be positive 1, and neutron will be 0, and electron will be negative 1. However, that is not the true charge. The charge is what, like 1.6 something times 10 to the negative 19th, and either that's in negative coulombs or positive coulombs, depending on whether it's a proton or electron. But seeing as how that only adds confusion and not clarity, we'll often just refer to them as positive 1 and negative 1. Just know that the charge of the proton is actually really small, the charge of the electron is really small, and they're just opposite and they cancel each other out. The masses of each, as you can see, are 1.0073. It's an AMU, atomic mass unit. Neutron is 1.0087 atomic mass units. Those are very small but very similar. And electron, which is much smaller, 0.000549 AMU. So if I were to compare these guys, it's something like close to 1,800 times more massive. 1,800 times more massive. So that's how they could know, like, oh, clearly the protons must be given a big chunk of the mass, because if they have a rough idea of what the mass should be, and this is 1 over 1,800, it's a big difference. But the protons and neutrons are located in the nucleus, while the electrons are within the electron cloud. So, as we refer to each element, there is certain terminology we'll use to talk about elements. The first one of which is the atomic number. When we abbreviate the atomic number, we'll often talk about this being as Z. The atomic number Z. Z. This atomic number is the defining characteristic of an element. An element cannot change its atomic number without completely changing its properties. Yes, some elements will have different numbers of neutrons. Some elements will contain different number of electrons, and it does change the properties a bit. But Mercury has 80 protons. Gold has 79 protons. Mercury is a liquid at room temperature. Gold is a yellowish solid. If I were to lose a single proton from Mercury, it would solidify up as gold. Regardless of the number of neutrons, it might still fragment. It might do some other stuff. The number of electrons, it might do other stuff, but it would cease to be Mercury if the number of protons change. So every carbon has 6, every nitrogen must have 7, every oxygen will have 8. Now, it is possible for them to have a different number of neutrons. A neutral compound must, in order to be neutral, must have the same number of protons and electrons. But it is not needed when it comes to the neutrons. If they have a different number of neutrons, it is said to be an isotope. Isotope means at the same place. So the same number of protons, but it's kind of different. That an isotope, for example, protium is the simplest form of hydrogen, one that has one proton, zero neutrons. If I were to give it a neutron, so it has one proton and one neutron, it becomes deuterium. It's one of the components of heavy water, often found in nuclear reactors. It is heavier because it has an extra neutron. It essentially doubled its mass. It is possible to have tritium, which has two neutrons and one proton. This is incredibly rare and usually only occurs in nuclear reactors and in suns, where we can have heavy bombardment and neutron captures. But this is very rare outside of those situations. And that is, tritium is incredibly unstable. So their properties change, but it's still considered hydrogen. You got other ones. You got chlorine, you got bromine, the well-known isotopes, boron. Not all elements have isotopes, but many of them do. When we talk about the isotopes, we can distinguish them by looking at the mass numbers, because the mass number is the sum of the protons and the neutrons. The protons and the neutrons are about equivalent in the mass, so we can just add them together. We don't need to typically consider the electrons. They are so small as to not really matter. So the mass number, A, is the sum of protons and neutrons. This is the number that when you're writing an element in this format goes on top. Now, if you look at the periodic table, the mass number is the one that will show on the bottom of the table. So they've switched places on the periodic table, but when we're writing this, the mass number goes as a superscript and the atomic number goes as the subscript. Now, we've talked about neutral, but not all atoms will exist as a neutral particle. Some will exist as a charged particle called an ion. Now, because of the fact that the atomic number, the protons, are intrinsic in the element, the atomic number cannot change. So we cannot lose protons. So the only way to become charged is to affect change within the electron cloud. So we are either going to add extra electrons to the electron cloud, or we are going to remove the electrons from the electron cloud. The nucleus will remain unchanged. Now, because electrons are naturally negative, we need to consider the implications of this. When we are losing an electron, we are losing a negative. We are subtracting a negative. When you subtract a negative, it is the same as adding a positive. So it becomes more positively charged. We call this a cation. The cation. Similar to cathode, the positive charge of the battery. When electrons are gained, we are gaining a negative charge, so our charge goes down and the atom becomes more negatively charged. We call this an anion. The anion, much like anode on the battery. Cathode, anode, cation, anion. Anion is negative, cation is positive. So now we can introduce the charge number to that formula over there. That A our mass number is the sum of the number of neutrons and the number of protons. Z is just the number of protons. And our charge, which is a superscript that goes behind it, is the difference between the protons and the electrons. If there's more electrons, we have a larger E, and thus the difference gives you a negative number. If we have less electrons, we get a positive, the Z is larger, and we get a positive charge. And if they're the same, they cancel out, and you get zero charge. So we can take that into account. So let's start looking at some practice. We should be able to do this. This should not be something that should challenge us. So with that in mind, we'll go ahead and take a look. I wrote these on a doc cam so speed things up. So remember, Z A charge. The first thing we can always do is find the number of protons. The number of protons is always the easiest. Now, if there is no charge, we know that the number of protons and the number of electrons must be the same. When it comes to the number of neutrons, we need to subtract the number of protons from there. So 7 minus 3 would have 4 neutrons, 3 protons, 3 electrons. With chlorine, 17. It's neutral, so it stays 17. But 35 minus 17 is... And don't feel you have to do this mentally. You can always pull up a calculator. 35 minus 17 is 18. 17 protons, 17 electrons, 18 neutrons. In most situations, neutrons will either be equal to or in greater concentration, in greater amounts than the number of protons. The only major exception is hydrogen. 15, zero charge, so 15. 31 minus 15 is 16. Most of the lighter elements have equal or slightly more neutrons, but as we get into heavier and heavier elements, the number of neutrons will greatly change. Carbon, so we have a 6. Number of electrons, we're going to have a 6. And 12 minus 6, we're going to have a 6. So carbon in its most standard form, 6 protons, 6 electrons, 6 neutrons. Well, let's look at potassium. So now we have neutrons. So now we have a charged molecule. So 19, that's always still the same. Well, potassium, so plus. So positive, so let's look. Positive 1 must equal 19 minus E. Rearranging this, so I'm moving that over there, moving that down there. E equals 19 minus 1, because I added E to both sides, and I had to subtract 1 from both sides. So the number of electrons has to be 18. 1 less, 18. And then, of course, the number of neutrons, 39 minus 19 means 20. But oxygen? Well, oxygen's 8. 16 minus 8 is 8. And it's 2 minus, so negative 2 equals 8 minus E. So moving that around, switch that around. So E equals 8 plus 2. How many electrons do we have to have? We have to have 10. 10 electrons. One last one. Iron, 26. 56 minus 26, we get up to 30 neutrons. We're really starting to get heavier. And with this guy, plus 3 equals 26 minus E. Rearranging that, E equals 26 minus 3, get 23. So 26, 30, and 23. This should be something we should easily be able to do. So, skipping there. Notice I put the electrons before the neutrons. It doesn't really matter. The important thing is you correctly label everything. Correctly label everything to let people know what is a neutron and what is the proton we're referring to. Okay. Another aspect of this is, so we talked about the atomic mass unit. Since these atoms weigh next to nothing, we need to introduce a new weight unit when dealing with single atoms. That is the atomic mass unit. Otherwise, we're dealing with picograms when it comes to that. And so it becomes very hard. Once again, all weights have to be standardized off of some number so that scientist Dr. Bob over in Washington, D.C. can do something with Dr. Laura over in Oregon, and Dr. Rajit over in India can all have the same numbers. They can all standardize it, do the same experiment, and come up with the same numbers because they all have the same unit for measuring a mass. So we have standardized this so that the main isotope, carbon-12, weighs exactly 12 AMU. And that mass is made by, you're essentially calculating the weight of all the protons, the neutrons, and electrons, and their relative atomic forces. So they weigh out one atom, and that weighs exactly 12 AMU. Now note, if you weighed up 6 protons, 6 neutrons, and 6 electrons, it would actually weigh a little bit more. That's because the 12 AMU has some strong nuclear forces that causes the weight to go down a little bit from the pure subatomic particles. Now, as I said, carbon should weigh 12. However, if you look at the periodic table for where the mass of carbon, you read 12O11. And this is because we are rarely, if ever, dealing with a single isotope. When we're dealing with a very large number of atoms, we must consider the weights of all isotopes involved. And so we do something called a weighted average. Now, the weighted average is an average where you take into account the relative number of atoms of each type of isotope. It would be like if you had an average of like 5 numbers of like 1, 3, 4, 3, and 5. Well, the average is going to have a greater portions of 3s in there than some of the other things, and so it's going to be closer to 3 than it would be to, say, 1 or 5. Now, imagine you did that, except you did 100 numbers, and 3 came up 50 times. Suddenly 3 is looking like a lot closer to the right number. Now there might be some higher, there might be some lower, but your average is going to favor 3 as the number that shows up the majority of the time. So imagine that, except we're doing that with atoms. So if we look at all of the carbon atoms and we compare how many times you get carbon 12, how many times you get carbon 13, how many times you get carbon 14, and you add up those ratios and average them, you get a number that looks like 12011. So the way they do this, the way they calculate the atomic mass, is they take the sigma, which is the mathematical term for sum. Get used to that. It will be used occasionally. Sigma, the sum of the fraction of the isotope times the isotope's mass. So we're going to figure out how many times out of 100 do we get this isotope and how much does it weigh. In this particular case, one of the most common ones is chlorine. Chlorine has 2 stable isotopes that are moderately largely abundant. We have chlorine 35 and chlorine 37. They have, with respect, a 75% abundance of 35 and a 25% abundance of 37. So, when you grab out an atom, the likelihood of it being chlorine 35 is a 3 out of 4 ratio. So if there's only a 25% chance, I will get a chlorine 37. I'm drawing a number line so we can better picture this. I'm going to jump to the document count. So I have these 2 numbers. Now, if I had a 50-50 shot, this is a 50-50 shot of having chlorine 35 and chlorine 37, your average mass would be 36. But as we move to a greater proportion of 35, we're going to slowly move to the left, so it's being more closely represent 35. So at this case, if my atomic mass was 35.5, this would be literally 75% this and 25% this. Because as a 50-50 from that 50-50, so another 50 of a 50 is 25%. So this is more closely resembles our number. Nope, wrong thing. So, with that in mind, bromine is another big one. Bromine 79 and bromine 81. These guys are almost evenly divided. We have a 51-49 atomic weight percentage. Almost that. Not quite that. But if you take their atomic masses, which is 78.918337, which essentially rounds to 79, and 80.9162906, which is approximately 81, and multiply by their relative abundances and sum them up, you're going to get the weight we see on the periodic table, which is 79.904. This is incredibly useful when we're dealing with large quantities of atoms, because we're dealing with billions and trillions of atoms. So the likelihood of getting just one isotope is very low. And so we have to take this into account. This is the problem. For example, if you've seen the movie Oppenheimer, they had to make the bomb. Well, the problem is the most abundant isotope of uranium is not particularly fissile. It's not easy to cause that to split apart and create the huge amounts of energy we need for the explosion. So they had to find a way, a method, to separate the trace amounts of the heavier uranium from the lighter, not nearly as reactive uranium. That was a large portion. They couldn't just find pure of this source here. So they had to take this uranium and find different ways to kind of tease out the heavier uranium. Usually people nowadays turn it into various compounds and use centrifugation to help separate this. You need very powerful centrifuges and a lot of complex equipment to do this. And so that's one way they can, but that's what they're doing. They need to separate to get as close to pure as they can. Now, before we go any further, we also need to talk about the periodic table. And I'm going to kind of slip this into this video because, well, there's not really another place to put it, and I didn't want to make another video. But so the periodic table, while this is regularly shaped, it was built to characterize elements. It was put together because reading the table tells us a lot of information about the elements. By looking at a table, you can know about their reactivity, their electronic structure, their approximate size, and some various other properties. That when we arrange things in the periodic table, they're arranged in periods, which is our rows, and groups, which is our columns. That each period has a certain range in sizes, and this is going to be due to electron count, which will come up in a few chapters. So, but essentially we have electron clouds that are going to build on each other like Russian nesting dolls. And so each time we go down a row, go down a period, we're going to add another layer. And so atoms are going to get bigger and bigger and bigger because we're adding another set. And so the limitation of what layer we can get to is defined by what row we are in. Groups, for example, will help determine reactivity. That lithium, which is above sodium, which is above potassium, rubidium, and cesium, will all react the same way when you mix them with water. Yes, the degree of reaction may increase as we go down the table, but they will all react with water to form a base and hydrogen gas. That there's a reason why copper and silver and gold are in the same group. They are called coinage metals for a reason, because they are largely not very reactive. There's a reason why that fluorine, chlorine, bromine, iodine are in the same columns, because they do a lot of the same reactions. They all exist as diatomics for the same reason. So one thing we'll learn about a little bit later, but we can keep in mind now, many of these elements were not discovered. Elements weren't discovered all at once. The way they're discovered is with bursts based on technologies. When we get a new piece of equipment, sometimes that equipment can lead to a great deal of work. If you can capture gases, suddenly you can separate air into its plenty of components. You find out, well, oxygen. Okay, if I can remove all the oxygen out, what do I have left? Well, you have nitrogen. Well, if I can tease out that, what do you have? Maybe you have some argon, you have some hydrogen. If you have different ways to test minerals, you can quickly figure out, like, oh, this mineral contains a new element in here. new mining methods, new analysis methods. All these things lead to suddenly we find stuff that were right in front of our face the whole time, but we didn't necessarily recognize them as such. So by 1865, only 63 out of 118 elements have been discovered, a little over half. So that means there's a lot of gaps. Now, mind you, a lot of the upper part of the table has been discovered, but there's still holes here and there. And if you're trying to put together a puzzle with missing pieces without even a box to look at for the picture, you're often going to have a hard time, especially if the puzzle is, like, say, blank, like we're doing the Beatles' White Album puzzle. Oof. Or like a starry sky where it's just stars twinkling out there. It becomes very hard to put things in the correct order. By 1869, two different chemists have separately created very similar periodic tables. Dmitry Mendeleev, who we recognize as the discoverer in Russia, and Lothar Meyer in Germany. There were others out there with kind of silly sets of elements, ones that we laughed off that were not quite there or just too preposterous to do. There was a scientist who had a musical scale of elements, so the do, re, mi, fa, sol, la, ti kind of thing, and many scientists found it too whimsical and they dismissed it out of hand. Now, keep in mind before you're like, well, this seems like an impossible task. They did know about atomic weights. They did have a rough idea of the atomic weights of an element. They didn't have the atomic numbers, which would make this so much easier, because you can clearly at least put them in order left to right. But atomic weights do help. 90%, maybe 95% of all elements, as we move from left to right, have an increasing atomic weight. Does that mean they all go in even bursts? No. Some of them even reverse. Like if you look at cobalt and nickel, they're both about 58 grams per mole. So if you were trying to just go by mass, it's going to throw you off. But because of reactivity, we could put them in the correct order. Now, what makes the early periodic table, Mendeleev's early periodic table, so special is because there were plenty of blanks in the table, but due to the knowledge of reactivity and the properties of the various elements that have been discovered, he knew to leave gaps, leave spaces for an element should go here. This element A, reacts like this element. Element C reacts like this element. It does not react like this other element, so we know there is an element B that we are missing. We know we are missing this element. We should find it. And so we can see here, this is our current periodic table as it stands. We have the alkali metals and alkaline earth metals in the first two columns, kind of like the front of the fort. We have the transition metals, kind of in a lower area, so walls of a fort. And we have a keep right over here, the non-metals and the chalcogens, halogens. And we have a separation line that separates the metals from the non-metals called the metalloids. And then we have the intertransition metals kind of placed down below like an airstrip. However, technically they're supposed to fit in right between the alkaline earth metals and the transition metals. The reason why we do not place them there is because then this table would become too stretched and would not easily be readable on a screen. So rather than try to push this outwards, And you'll notice this table is actually not even completed. We have actually completed all the way to element 15, 16, 17, 118. And they've been named at this point. However, those elements are so rare, I don't really care. Not really. They are man-made elements, so it doesn't really matter to that extent. But some of these elements have properties we can look at. So when we talk about metals typically share these properties with each other. They have luster in their pure elemental shape, so it means they shine. They have a high degree of conductivity, whether this is conductivity of heat or conductivity of electricity, which is why they use copper wires and aluminum wires in electrical outlets, because they conduct electricity very well. It's why we use iron and steel and all sorts of metal containers when it comes to heating things, because they conduct heat very well. And all of them, except for mercury, are solid at room temperature. Many of these are malleable and ductile, meaning malleable, they can be hammered into shapes, and ductile, meaning they can be stretched into wires. Essentially, you can peel off the atoms into a wire, into a long, thin strip. Now, our nonmetals, on the other hand, are very opposite properties. They are typically non-lustrous, so they're like dull. They're often non-conductive, in that they don't conduct electricity or heat very well, except for certain examples. Like diamond doesn't conduct heat, doesn't conduct electricity. Yes, I know graphite does. That is a unique form of carbon. And they exist in all the various different states. There are some liquids, there are some gases, there are some solids. A mixture of all the two. Now, our metals are typically positively charged, and our nonmetals are typically negatively charged. And we'll talk about why that is later. And in between, we have the metalloids, which means they have metal and non-metal-like properties. That nonmetals typically like to form covalent bonds with each other. Silicon, similarly, likes to form covalent bonds in a similar way to carbon. However, it conducts electricity far better than carbon does. It's very similar to that of a metal, which is why silicon is used as a semiconductor in chips and in electronics. So with that in mind, that's where we'll stop for now.